Hi everybody, how you doing? I hope everything is good out there. Miss ya. I hope things are going all right. All right, so we're in the unit 2 and we're going to do a couple of things in this video. But first, can you find the mistakes in these two problems? Go ahead and pause it and see if you can see the mistakes in my work. All right, go ahead. All right, did you see it? Now, the first one, the big mistake is the unit mismatch. That's a big mistake. I call that the unit mismatch. 15 minutes, right? That's a quarter of an hour. And if your time is in hours and your speed is in miles per hour, this should be x plus 1/4, not 15. All right. So I just set up the first couple steps here, but that really should be there. Now, in the second one, there's a couple of mistakes. We actually did a problem really similar to this. But one thing that you may not have picked up, hopefully you picked up on this, the amount of water evaporated. This should be a minus, right? Because it's evaporated. The other very subtle mistake is the amount of solution should be here. Okay. And the amount of acid should have unit on it. All right. Those details are important. Don't forget those. Make sure you're collecting questions to ask about on next week. Okay. All right. So jumping in, you guys did your functions discovery activity. You know what domain and range are. We're going to practice writing them from graphs. We know that the domain is the set of all the x values of a function. The range is or a relation, and the range is the set of all the y values, the outputs of a function or relation. So let's check out the domain of this one. We see that if we go to the x on the x-axis here, everything from -3 to -1 is covered. But notice how -1 is included, but -3 is not, right? Now we make a jump, right? And you can even trace it to the x-axis here. We make a jump from 1 to 3, and those are included and are part of the domain. So the range in this case, right? Now, this is something that people mess up a lot, right? You can see that if you scan, and if I took a horizontal line, not a very good horizontal line. Let me try that again. I'm sorry. If you took a horizontal line and you scanned it and moved it up, right? Now pretend this is horizontal. We can see that starting at -5, you have a y value. These repeat starting here, right? Well, technically past -2, they repeat, but it doesn't make sense to list the set of all the y values more than once. For example, -1 occurs more than once, but we don't list it more than once. So we'll list everything from -5 all the way up to 4, right? Because all of those y values are present. Now, I'm using interval notation. You don't have to, right? You can, of course, use set notation, and actually once we get to the repeated pattern ones, we will use those. We will use that. But for now, interval notation makes a lot of sense to use. All right, this one, actually a little bit simpler. Our domain here is starting at -2, right? That is the smallest x value, right? All the way through infinity, right? This is clearly going on forever to the right and moving in the positive y direction forever, right? So we could also say that the lowest y value is -2 up to infinity. So the lowest y value right here is -2, and every y value is covered by this function. Okay? The open circle, closed circle is what I use to determine, right, whether I'm going to use the included or not included, right? Okay, so let's do Now let's get into some of these ones that are a little bit funky, all right? So here I look at it and I'm like, oh, wait a second, the domain of this, okay, sorry, the axes are not great in this one, but I'll make the axes here. Okay, so starting at -3, all right, I have my function, but now I see this and I'm actually, let me use red. -3 is the lowest x value. However, -1, you might be thinking, oh, -1, I should stop it there. But look, trace it up, right? -1 is an x value that is it's part of the domain, right? If you trace it up, it actually is in this part. Now, if we continue over, once we get to 3, 3, if you were to do f of 3, for example, you wouldn't use this piece, but you would use this piece. 3 is an element of the domain of this function. So you can go all the way to 5, and even though there are breaks or discontinuities in this graph, every x value from -3 to 5 is part of the domain, right? You can find it somewhere on the graph. Now, things get funky with the y values, right? Ask yourself for a second, how many y values are present on this function? If you said 3, right, you would be correct. You would have y such that y equals only 3 values, -2, 1, and 4. And this is set builder notation. Why would I use interval notation when it's not an interval? These are discrete numbers. There are only 3 numbers, whereas the domain contains all of the real numbers, including -3 through 5 non-inclusive, right? So whenever I'm listing out, you might want to write that as a note. When listing out a discrete set, meaning you can count the numbers, so -1, -2, 1, 4. Use set notation. If you are describing every number in an interval, obviously use interval notation. For example, the domain here contains, I don't know, -2.812423, right? Every real number is contained in that interval. Sorry. That interval contains infinitely many real numbers, okay? All right, so the domain for this guy here, same idea, -4, right? If you trace it, you can see that everything gets closed up, so we're going to go all the way to 5. And the range contains exactly 3 values again, and this time it is y such that y equals -2, 1, and 3. Even though it contained infinitely many times, those are the only y values you would have. Okay, so now let's talk about these continuous pattern functions. Now, I have to tell you, right, that in the following, we're going to assume that these patterns continue forever, right? We can't do it with arrows because it doesn't represent the pattern appropriately, right? There's no way for me to say like, oh, I'm going to put an arrow on the line, it doesn't make any sense, right? You can only use an arrow for a function that is not discrete, for example. A function that has all the values, right? There are no breaks. You don't have to lift up your pencil. But anyway, let's list out the elements of the domain to start. So I start by doing this. I'm like x such that x equals, what I got, -3, -1, 1, 3, and then suddenly I realize I can't stop, right? This pattern's just going to continue, right? Off of this graph, somewhere here, it's just going to keep going, 3, 5, 7. But I also have to realize that it goes on forever in the other way. This pattern continues forever in both directions. Okay? So technically it would be like this. Now this is not really how we would write it, right? The way we can model this is what I call with a start and jump. Okay? Now the good news is you can start with anything. So typically you can start with 1, right? So if I started with 1, right? The jump that I'm making is 2. Hopefully we realize that every time we do this we go 2, right? So 2, 2, right? 5, 7, 9, whatever, right? So if I add 2, I get the next one. If I add 4, I get the next one, or the one after that, right? If I were to add 6, I can keep going, right? So adding 2, adding 4, adding 6 from 1 will give me all the values, or subtracting them. So the way we represent that is we say something like this. We say 1 plus 2k. Now k is a constant, right? K is a, no, I'm sorry. K is kind of the number of jumps, right? K is something that we can use to represent any jump in any direction as long as k is an integer, right? And this symbol means integer. So for example, 1, 2, 3, 4 are values of k. But -1, -2, -3, those are also values of k. Technically 0 is a value of k as well, right? And now I can write x such that x equals 1 plus 2k, where k is an integer. Okay? Now the nice part about this is this can vary. This 1 could have started from anything on this list. Right? Could have been any element, because if you started at, say -3, you could add 2 in either direction forever to generate the whole set, as long as k is an integer. That is very, very, very important. Okay? It must be an integer. If you added a fraction, for example, you're not generating that exact set of numbers. Okay? All right, let's check it out for range. List out all the elements. I'm sorry, that should say range. Okay? So now I start to do the same thing with the y's. I'm like, okay, I see -2, -5, so y such that y equals -2. Oh, sorry. Let me go from -5, -2, 1. As you can tell, I'm making a lot of mistakes because I'm a little sleepy. The new baby tends to keep you up, but I'm okay. Okay, so we go in every direction, either direction, up 3, down 3, 3 forever, right? So how do we model this pattern? Well, we can model it in a similar way, right? If I say to myself, all right, y such that y equals, and I start anywhere, so let me start with -2 this time, right? So I picked this element. As long as I make a jump of 3, and I can use k, right? K is kind of what we tend to use. Technically, I could use any variable, any letter you want, any jump that you want to make, k, m, p. As long as k is an integer, you're going to generate this whole set. Okay? So you could have picked anything else, and I'll rewrite this down here for you. Okay? Alright, after a while you get the hang of this. This isn't too bad, okay? See if you can, I think I gave you, yeah, I gave you, I want you guys to try 2, 3, 4, 5, okay? And then we'll talk about function notation. Go ahead, pause the video, try 2, 3, 4, 5 now. Let's see how you do. Okay, so for the domain, one possible answer, and it's not the only possible answer, is something like this. Right? Now, the thing that could be different here is the 2. You could have picked -3, you could have picked 2, you could have picked 7, you could have picked -8. As long as you make a jump of 5, because that's the jump, you're going to be fine, right? And as long as you put this in, you're going to be fine. K is an integer, right? Now, for the range, right, I would just do this. Okay, now all this says is that y is an element of the integers. Technically, I am guessing a lot of us had something like this, maybe 1 plus 1k is an element of the integers. But this is just a kind of a long way to write this, right? You're just saying that this is, I'm starting at 1 and I'm adding 1. Well, you're just generating the integers, right? If you look in the graph, the numbers are 1, 2, 3, 4. And again, we assume these patterns are repeating. These entire problems, 1, 2, 3, 4, 5, are all repeating patterns from here on out, okay? So I would just say this is the integers, okay? We can talk about that more. Hopefully for this one, you got this. And this might be another one where you're like, Mr. Cat, I started at 3. Can I do that? Well, if you start at 0, right? So maybe you add 0 plus 3k. If 0 is one of the elements, you don't need to write it, right? The set of all the numbers in this domain is 0, 3, 6, -3, right? -6. It's just all the integers multiplied by 3. Right? So that works pretty well. So don't write it if you don't have to. Okay? This one, though, right, the range, and I'm so sorry I wrote y instead of x. That's my fault. Okay? This one, the range is y, so that y equals -1 plus 4k, where k is an integer. I chose -1. You could have chosen 3 or 7 or -5 or -9, and they all work, right? This -1, I chose it from here, but you could have chosen that. Okay? Okay, folks. Now 5 is something you probably should have gotten similarly. This is another one where if the pattern repeats, x is an element of the integers, right? And the range, y, such that y equals, I'm going to say 3 plus 5k, where k is an element of the integers, right? But hopefully you realize that you could pick anything else, right? As long as it's one of these y values, -2, 3, 8, 13, you're going to get all the numbers, right? This one is a little funny, number 4. So technically, to make this better, I'm going to put a closed circle here. This is called a step function. This is a really classic function in math. But this is a step function. And technically, we see that every single element is present in the domain here. Right? Every single element, assuming this goes on forever, again, you can pick any x value. Pick this x value, right? If you were to trace it up, you would find it somewhere here. This x value, it's right here. This x value, it's right here, right? Notice how it has to be the closed circle that gets the point. Because if you had two closed circles on a vertical line, suddenly it's not a function, right? We're talking about functions. So the domain is all the reals. Every single x value is taken care of. The range, though, works in the same way that these other ones do, right? You still have this, y such that y equals, I don't know, -1 plus 3k. k is an element of the integers. Okay. All right. See how you do with those. There's a lot of practice with those type on the worksheet, and you can kind of go from there. All right. Also in this video, we're going to do a quick intro to function notation, ways to represent functions. All right. So this right here, that's just the name of the function, right? When you see f of x, right, you can have p of x, g of x, h of x. You can have temperature of x, right? Sometimes you're going to see a whole word written out, right? Depending on the textbook, the worksheet, the publication, right? All different ways to name a function, but that's the name of the function. Okay? This x is your input, right? It's not the domain, okay? The domain is the set of all the numbers that you can input into a function, right? But just calling that the domain doesn't make much sense, right? It doesn't, saying something's f of x doesn't say all the numbers you can put into it, okay? This taken together, this is the rule, right? If it's written algebraically, this is what you do to it. For example, if I were to put f of triangle, it's telling me to take 3 triangle plus 4. Whatever I put in here, it's telling me multiply that input by 3 and add 4. The x is really just a dummy. It's just telling you what to do to the input. F of blah equals 3 blah plus 4. Okay? And the last thing we want to do is interpret this entire thing as the output. Right? So what you really get when you do this up here, for example, is you get a statement of two things that are equal. This thing right here, f of triangle, equals 3 triangle plus 4. So f of 10 equals 3 10 plus 4 tells me something. It tells me f of 10 is what, 34? Meaning that the output, right, I can interpret this as the output when the input is 10 is 34, right? Or to say it more, the output when the input is 10 equals 34, right? So it's really stating the element of the range corresponding to that 10 in this case, which is an element of the domain. So I know you kind of know this, but it's important to remember it because when you deal with functions inside of functions, when you deal with a lot of functions, when you deal with inverse functions, all things we're going to look at, you want to keep that in mind, okay? Keep all of this in mind as we go, all right? Okay, so some quick examples, right? Remember, a graph like this is just a way to represent all the input, output, pattern behavior from an algebraic function, for example, right? They're not all necessarily algebraic functions, but when you have an algebraic function like this, negative absolute value of x minus 3 plus 2, the graph is just representing all the coordinate pairs of inputs and outputs, right? So f of 2 is just equal to 1, right? This graph is telling me when I put in 2, the y value is 1. When I put in 5, it is equal to 0. F of 5 equals 0 because the point 50 is on the graph, right? When I input negative 4.5, well, you could kind of figure out where it's going, right? But maybe if you don't see it on the graph, I'm going to do negative 4.5 minus 3 plus 2 equals negative, what is this, negative 7.5 plus 2? So I get 9 point, sorry, forgot the negative out in front. I get negative 7.5 plus 2 equals negative 5.5. So that tells me that the point negative 4.5, negative 5.5 is on the graph. So what about these? Find all the values of x for which f of x equals negative 1. Well, that's giving me an output, right? Hopefully we see there are two x values. I like to write these in set notation. X equals 0 and 6, right? Those are all the x values that would give me negative 1, right? F of x equals 1. Okay, there are two. We actually know one of them from right here, right? But we know that x equals 2 and 4 will give me 1. We know the 2 already, but we can see the 4 from the graph. F of x equals 2, well, this time there's only one of them, right? Right. By the way, you could check this by plugging it into the algebraic equation that we got, and you would get 2, right? And hopefully we see that f of x equals 4 has no answer, no x value, right? And hopefully we see that if we set f of x equal to 4 and tried to solve it, which we could have done with all the others, by the way, we get something that is preposterous, right? Divide each side by negative 1 gives us this. You get negative 2 equals absolute value and nothing else. You stop right there. It's no solution, right? So there's the connection between the graph and the formula, which again, maybe you know, maybe it's kind of new, maybe this is like you're really good at this already, but it's important. We got to make sure we're really, really good with it. Okay, one last thing, and then you can do some practice. Let's do this one real quick. F of 2, right, is negative 1. F of negative 5 is 6, right? This is just review, right? Negative 5 is 6. For what x values is f of x equal to 2? Okay, well, I look, oh, so that's a y value. It's going to be 11 and negative 3. Again, I like to write that in set notation because it feels like I'm solving an equation, right? For what x values is f of x equal to 0? Well, this time there are 3. This is when is the output equal to 0, essentially where are you on the x-axis when you're talking about the graph, and your answers are negative 2, 5, and 12. All right, so for what x values is f of x greater than or equal to 0? Here's where things get interesting, right? So I look at this and I'm like, okay, f of x was the outputs. So where's the output, which is the y, greater than or equal to 0? Right? And I'm like, wait a second, right here. And right here. That's an interval, right? And this is where I would want to express it as an interval. So I've got negative 5 to negative 2, right? Union 5 to 12. Now notice how I included 5 and 12 and negative 2 because it's greater than or equal to. In this one, right, this is, let's pick this color. Where is it less than 0? Well, that's everything else, but I'm not going to include negative 2 and 5, right? Right? Because at negative 2 and 5, we know it's equal to 0, so don't include it, right? And we will include 13 because that's definitely negative, right? And it's part of the graph, right? And then last but not least, what's a domain? Well, full circle back to the beginning. Domain is negative 5 to 13. Every number between that is included. And the range from high to low, from low to high, I'm sorry guys, I'm really sleepy. That was from -2 to 6, right? Even though some of those values are included more than once. Okay? I hope this helped. Try the other worksheet. Again, we'll answer any questions when I return. But hang in there. Have a good weekend if I don't see you. Bye, guys.